All right, good afternoon, everyone. And I hope everyone is doing well wherever you are. And yeah, I think hopefully more people are gonna get here, but we started our recording already. So it should be fine if people need to catch up later as well. And so today the plan is to, I think we should be able to finish chapter 7, Bayesian inference for a proportion. What's left is mostly about what kind of Bayesian inference techniques you can do when you know already the posterior distribution is a beta. So let me bring up the slides and then we can go from there. So if you remember what we did already was mostly, let me get to this point. Yeah, so we motivated us using the restaurant survey example. And then we talked about what if you have discrete priors for proportion. And this is using the D by norm, a lot of places in order to do the discrete version of the Bayes rule. And then we introduced this beta distribution as a popular continuous prior for binomial data model. And we learned that, well, last, I guess, Wednesday, part of it was a little bit complicated of doing the derivation and all that, but we showed you two different ways, right? One is to not worry too much about the constant, mostly just thinking about the terms about P, and then eventually we'll be able to recognize the posterior to be another beta. But we also did another version, which we won't do as much as you will see. The other version that I mentioned is mostly how to keep the constant and then making sure that eventually we do arrive at what we claim the posterior would be. So like I said, most of the cases in the future, we won't be worried about those constants. What we did on Wednesday is really trying to justify that indeed, even if you don't deal with the constants, you arrive at a posterior that we claim it should be. And most often with the continuous prior, we're going to work with what we saw, the proportional sign of the Bayes rule of the continuous nature. And moving forward, that will be the focus that we're going to have as well. But every now and then we might do a little bit derivation and just to verify the results as we see it. But more often not, like I said, we'll be working mostly with the proportional version of the Bayes rule, the continuous Bayes rule. So the last part of this whole chapter is just to talk about a few inference techniques, I should say inference questions that you might have, and then what kind of techniques we have to do those questions. So the first one, the general category, is Bayesian hypothesis testing. So in other courses you've taken before, I'm sure you know about the general setup of hypothesis test in the classical or frequentist framework. So for us, the Bayesian hypothesis testing is once again about that unknown parameter P, right? And before we collect data, we have some prior. After we collect data, we have a posterior. So all of the tests itself are going to be surrounded around how we understand the posterior distribution. And you will see that for other inference techniques, we do that as well. So for example, to get us started, suppose one of the Tokyo Express's workers claims that at least 75% of the customers prefer Friday. The question is this a reasonable claim? So remember, P is the proportion of people or customers preferring Friday. And if we look at this question itself, or this testing question itself, pretty much we can figure out what is the probability that P is greater or equal to 75%. Okay, and we're able to do that because we have a understanding of the distribution in the posterior about that P. So pretty much we know what the P is. If you remember, in the discrete case, we're just adding up. If you remember, like those rows when P is greater or equal to 75. And then when we're dealing with continuous prior, which we're going to focus on right now, we already know what the what the beta posterior distribution is, like the new A's and the new B. With that, we should be able to summarize the posterior probability that P is greater or equal to 75%. So with that, I just want to show you, it's pretty much just finding the posterior probability. So it's the probability of P of greater or equal to 75%. And then you can make a decision based on the value of the posterior probability. If it's high, you will, I guess, support the claim. If it's not very high, then you're going to reject the claim. Okay. So how to do that? There are multiple ways to do it. The Pro-Base package that comes with the textbook itself has this beta area function that can be useful. So here you can see that they have a few inputs. You can do LO. LO stands for lower or low, and then HI stands for high. So we're pretty much just trying to find the area under the curve of this beta distribution that is between 75% and 100%. So the shape underscore par that gives us, or I should say, we need to supply the values of the posterior shape parameters. So following that example, we have 15.06 and 10.56. And then the last argument color, you can choose whatever you use. And I was using this particular blue color. And every code, again, is in the markdown file that I uploaded. So you can play with it to get similar or different variations of this overall plotting or I guess visualization. So you can see that the beta area function at the top, I mean the figure at the top of the figure, they also give you actually the posterior probability, which is pretty small, as you can see, it's 0.04. So what that says is the posterior probability of this statement that p is greater or equal to 0.75 is only 4%, and you can decide to reject the claim. You can see here that we haven't talked much, and actually in general, people don't talk too much about like a cutoff point, like is it like 5% or whatever, just like the significance level concept in the frequentist approach. For us, really, I think 4% is usually considered as pretty low anyway, so we won't like discuss too much about exactly when to or where to do the cutoff, but for this example, remember that 4% is overall pretty small, so we're going to reject the claim. Here's a quick exercise. What about a claim that at most 30% of the customers prefer Friday? I'm not sure if everybody, so first of all, this is slide 37, so you should have access to it, so you can download once I put it, or you already have it if I put it into a breakout room. But I'll also say, if you want to try it out on your computer, make sure that you load, install and load the Pro, P-O-R-B. Let me type in the, or just write it over here. The package, some of you probably play with it already, but if you have not, because this function comes from this package, so you need to make sure that you install and load it before you want to try. But nevertheless, for this discussion question to work in the breakout room, it's not necessary like you get the final answers itself, but it will be at least useful to talk to your neighbors once I put it into the breakout room to discuss what, like, if you're going to use the beta area function, how you're going to use it and everything like that. Okay, so once you get that, I think it will be sufficient as a discussion in class. So with that, I'm going to create the breakout rooms and invite you back in about 2 minutes. Recording. Yeah, so on this, anybody wanted to share, maybe you already typed it out using the beta area function and got an actual probability. Even if you don't, we can describe what you would what we could have done for doing using the beta area function to understand or to answer this question. At most 30% of the customers prefer Friday. Anyone?
We didn't like work it out per se, but I just mentioned that at least for the code, we would have the low at, I guess, 0, and then the high at 0.3.
Yeah, perfect. Yeah, and you can keep the same, well, we will use the same shape parameter as before because that's the posterior. So yeah, I didn't calculate myself either, but I would say that will be the way to go. So you set low to be, okay, I can write it down over here. The low should be 0 if we're trying to answer that exercise, and then the high should be 0.3, sorry, 0.3. And then a different graph will show up, and then a different number and everything will show up as well. Okay, okay, sounds good overall. Cool. Okay, so there are other functions you can use, and as you can see that this beta area is particularly from a package that is accompanying the textbook itself. But there's also, maybe some of you know, and I think it's actually one of the homework questions for homework 2, is that there are various beta functions that is in the basic R packages. So for example, if we try to actually just try to get the area under the curve between 0.75 and 1, we can also use the P beta function. Okay, so the P beta function gives us, so I guess the input has 3. So here you can see that we're taking, so the last 2 are the shape parameters of the posterior beta that we're working with. And the first input for P beta, you can think of it as you input the percentile, and then it gives you the probability, or I should say at the CDF up to that point. So if I do that for 1, that's the last point that I have, and I minus that at 75%, that will also give me the area under the curve between 0.75 and 1. So this is, if you don't use the beta area function, you can use this P beta basic R function, and that should give you the same result, or very close should be. Okay. And I actually want to also mention we're able to do this because we already know exactly what the posterior distribution is. We know it's a beta. We know it has the parameter, shape parameters 15.06 and 10.56. And because of that, either the beta area function or the P beta function, you're able to use, and later we're going to see other examples of the other types of beta functions in R that you're able to do, as long as we know what the posterior distribution is. And indeed, this is what we assume what we have right now, because the beta distribution is a conjugate prior, like we talked about, because you start with the beta prior with different shape parameters, and you end with a beta posterior with another set of shape parameters. But as long as you know what the shape parameters are, you uniquely know what the shape, what the distribution is. Okay. So this will continue for a little bit, as long as we know, like say next chapter, we're also going to talk about an example when we're trying to make inference about the mean parameter. We could also build up some kind of conjugate prior if we do. And then when that happens, you would know exactly what the posterior distribution is. And you can do something similar like what we're doing over here to summarize the posterior by answering questions. But if you don't, later on, you will see that. But in addition to doing exact solutions, so we call them exact solution because we know, and we are using beta related functions directly to get those answers. But there's another whole area of approach of doing all this kind of summary of posterior, which we'll see more coming up as well. And this is trying to, instead of doing the exact solution, we can try to approximate the solution through what we call Monte Carlo simulation. And I have a set of slides for next chapter specifically to enhance our understanding about Monte Carlo simulation later. But for now, let's go through some of the examples. And I think as you see a few examples, it will start to make sense of what exactly we're doing. So the exact solution up there, like I said, if we don't worry about the beta area, because that's very specific from a particular package, but the P beta function, like I mentioned, is the exact solution because the P beta is getting that CDF up to a particular point that you are trying to evaluate, and that is the exact solution. Okay, just like the P norm that you usually use. This is for beta, so we do P beta. Monte Carlo simulation use what we call, well, it's called simulation. So the approach is that we actually going to try to generate a large number of beta draws from this known posterior distribution. And then we're trying to summarize in the posterior, or among all of the draws that we have, how many of them are greater or equal to 0.75. And we do that as a proportion, and then that it will be approximation to the true probability between 0.75 and 1. Okay, so with that, I have a few lines of code over here. So capital S, I use that to represent the number of Monte Carlo simulation draws we're going to do. Usually you want something large. And for illustration purpose, I think for our simple examples, like 1,000 will be definitely good enough. And you can explore other numbers as well later. So you specify how many draws you want, and then you can use the R beta. So R stands for random draw. So what we're doing over here is that we're taking random draws from the beta distribution. We're doing it for S number of times. And don't forget your shape parameters A and B of the posterior that we worked with. And finally, so remember in this beta samples, we have 1,000 different draws from that beta posterior distribution. And because we want to calculate how many, or the percentage of this 1,000 draws, how like the percentage of that is greater or equal to 0.75. So what we can do is we can do a numerical, or I guess a logical operator over here. We're checking how many of the beta samples, there are 1,000 of them, how many of them are greater or equal to 75. So within this paragraph, within this parenthesis, let me actually do that slightly better. So before applying the sum function within it, as I said, is a logical operator. So it's going to be binary outcome, either yes or no. Okay, so if it's indeed greater or equal to 75%, then it's going to be recorded 1 for that particular element. So this is a whole vector beta sample. So we're returning a vector of zeros and ones of the length of 1,000. And then we're taking the sum of them, meaning that we're counting how many of them are indeed greater or equal to 75%. And then we divide it by the total number of the draws that we have. So this gives us a approximated probability. Okay. So once we do that, as you can see, well, we might not have something as good as approximation over here. When this happens, I think usually you would like to increase the value of S. Usually, the larger the S value, which is the number of simulations you do, the closer the approximation to the analytical or the exact solution. Okay, makes sense? Yeah, so both approach, we like to introduce them here, mostly because, well, when you know the exact posterior distribution, like as a beta, you can use either one, it's fine. But this is the first time that we introduce the Monte Carlo simulation, as later on, you will see that sometimes we don't know the exact solution, and we need to kind of rely on simulation to help us to answer those inference questions. And here we know it, so we can actually use both method and compare as a way to verify that what we're doing at least seems to be correct. Like I said, the discrepancy between those two, I think are mostly because this S is not big enough. Okay. But other than that, we should be getting something close. So that's one type of inference question. If you have a claim about the unknown parameter that you want to test about, and for us, because the unknown parameter now, we are describing it using a probability distribution, especially in the posterior after we combine the data and the prior. So we can actually directly trying to work with the posterior distribution itself to answer a specific testing question. So another type is what we call credible intervals. Okay, so you see that this might be new to some of you, especially the term, because in the frequentist or classical inference, we call those intervals confidence intervals. Okay, for us, Bayesian credible intervals, we specifically mention it as credible intervals because once again, as you will see, we're trying to summarize something about the posterior distribution of the unknown parameter, and we're directly describing the parameter itself as a probability statement, just like the hypothesis test. Whereas confidence intervals, as you know, is usually a little bit convoluted. You have to say that, say, I'm 95% confident that the true whatever parameter is between this value and that value. And we know that that confidence itself, or confident, that word itself, is not about probability itself. It's more about if you're able to repeat a process that many, like a large number of times, then say 95% of the time, you'll be able to cover the truth. Whereas for Bayesian credible intervals, it is directly probability statement. Okay, so let me give you an example. Considering an interval that we're confident, well, I'm using the word confident, but it's really just like the interval that exactly have a probability of containing the P itself. So this interval like this can provide us a uncertainty estimate for our parameter, in this case P. And for example, a 90% Bayesian credible interval is an interval contains 90% of the posterior probability. So once again, it's different from how confidence intervals are interpreted. Here is really whatever value or whatever level Bayesian credible interval is indeed an interval that contains that value of the posterior probability itself. So how can we do that? The prob-based package, once again, has a handy function. It's called beta interval. And you can see that, well, again, it has the color, it has the shape parameters input, and it also just has one additional first input over here. It will just be the level of the credible level that you want to get. So here, if we want to get a 90%, we just put 0.9 over here, and then you have your regular shape parameters input, the color and everything. So once again, that will give you a printout of what the lower bounds and upper bound should be, as well as a graph. Okay, so this is the 90%. The 90% of the posterior probability is between this 0.427 and 0.741. Okay, so that's how you can usually interpret the results. And also a little bit caveat over here. This beta interval function itself actually only, I should say, they only have the functionality to return the middle, whatever level you're looking at. So here, as you can see, it's kind of like symmetric. We're having 5% on the left and 5% on the right in terms of getting the interval itself. And so maybe quickly here, instead of putting you back into the breakout room, if instead of 90%, I want to do a 98%, everything else stays the same except for the first input. I just need to adjust it to be 0.98. And as we know, for a wider or like a higher level interval, higher value of the level itself, we're going to have a slightly wider interval. And if you tried it out using your computer later, I think you will get something a little bit wider than the two bounds that we have over here. So the lower bound should be smaller than this 0.427, and the upper bound should be greater than this 0.741. Okay. So hopefully straightforward enough, and make sure that we know this is different from a confidence interval. This credible interval that we're doing is exactly, we have this particular range that covers the middle 90% of the posterior probability. So just like the hypothesis test, you can use like beta interval or beta area from the Bayes package, but there are other functions out there that you can use in R. Maybe you have some experience before. So let me show you a couple of other options and also discuss a little bit of caveat about like the middle or not necessarily the middle 90%. So once again, we introduce the exact solution, where you can do with the beta interval. Okay, so that's the line that we did before. And like I said, because of the way that the function is written, it only returns you the middle 90%. However, you can use the Q beta function, okay, if I want. And so for example, if I want to know the lower bound and the upper bound, I'm getting the quantile. So pretty much this is getting the cutoff value of the quantile. So if I want the middle 90%, I need to have the lower 5% and the upper 95%. And then I concatenate themselves, the two together, so I get the credible interval in this way. Okay, so once again, the Q beta takes 3 inputs. We have the shape parameters for the second and third. And then the first input, it is the percentile that you're working with, and then what it returns is gives you the cutoff point on the x-axis. And when I say not necessarily 90%, the middle 90% is, well, maybe sometimes you don't want to get exactly the middle 90, but you want to get, I don't know, like the left 90. So in that case, you can set this to be 0 and this to be 0.9. And that will still be an interval, you know, covering the 90% posterior probability. It's just not symmetric or anything. So there are different ways you can do it. Usually people, I think, just report the middle ones because it's kind of symmetric and kind of make most sense. But who knows in what situation you might not want to exactly return the middle one, but slightly different. In that case, you should be using the Q beta function instead of the beta interval, because the beta interval can only give you the middle ones. Okay, so with the exact solution, you probably notice I do this parallel stuff. So we can also introduce how you can do that with simulation-based. Okay, so simulation-based, just like the hypothesis test before, we can actually generate a large number of beta draws. And then there, we're just like counting how many of them are greater than 75%, because that was the claim that to be tested. Here, we're really just trying to do that for a large number of times, and then get the quantile at the lower, in this case, let's say 5%, and the quantile at the upper 95%. And in that case, we'll be able to get a middle approximation of the middle 90% as well. So if you do that, something very similar, we have the number of draws that we're getting, okay? And also beta sample, this is actually the same as before. We are generating 1,000 draws from this known posterior distribution, and we are using the R beta. Okay, so keep in mind, R stands for random draws. So whenever you're doing kind of simulation-based inference approach over here, you're most likely going to do random draws of the distribution. And so for us, once you get 1,000 draws, we're really just trying to get the quantiles, you know, the cutoff points numerically. So you can use this quantile function. I think some of you probably have experience from before working with this quantile function. So all you need to do is you get the draws like as the vector into it, and then you specify the quantiles that you're working with, and then that will return you a credible interval over here. So you can see that it's pretty close, okay? Like I said, if you increase the value of S, I think the approximation, which is the lower part, this one, This one is the approximation through simulation, should get even closer to the true exact solution over here. So at the end of the day, like I said, if you know, which is what we know here, the posterior distribution, you know the shape parameters for the beta. So you can either go with the exact solution or go with the Monte Carlo simulation. And this is actually a good way to verify that the two should get pretty close if you have large enough simulation samples. And this hopefully can justify later on, like I said, when we don't have exact solution, when we don't know what exactly the posterior distribution is, we kind of have to only rely on Monte Carlo simulation or some other simulation. Hopefully this gives us some justification that even in those kind of cases, the simulation approach will give us a relatively good answer. All right, the last part, maybe the most interesting, I should say, is Bayesian prediction. And I would say prediction is a very important concept, as well as an important, I guess, task of doing any kind of statistical method. And because you can always like trying to understand certain questions, doing like hypothesis test and maybe credible info, like what we did earlier. But a lot of times you can make prediction, or you should, or you want to make predictions based on the model that you fit. So we're going to introduce generally the Bayesian prediction framework. And I will also show you a concept that we can actually rely on Bayesian prediction to actually check how good our model is. Okay, so we're going to cover all of those today. So the prediction, let's set up with this toy example here. Suppose the Token Express owner gives out another survey, let's just say instead of N survey or customers, this time the survey is to N number of customers. And we're just curious how many would prefer Friday. Okay, so this will just be what we call prediction, because if you remember previously, we have generically I think N is the number of survey respondents, and then Y, right? Let me write it down. Y is the number of preferring Friday. Okay, so what we're trying to do is, well, the prediction, again, prediction is about the data points, okay? It's not about the parameter or anything. So that's why we call prediction here as how many would prefer Friday. We're interested in out of N number of customers, the Y, okay, in that case. And just to differentiate what we had before, I put a little tilde at the top of Y here. So to indicate that this is the predicted value, or the value that we're trying to predict. And what we had before is, again, capital Y is the random variable, little y is the actual data itself. So the predictive distribution, as you can see over here, is that we're looking at a predicted distribution of the Y tilde, the predicted value given the actual value that you have in your data sample in the first place. Okay, so this story is pretty much, you can think about this owner gave a survey before to N customers, and little y, number of them responded yes to Friday. And we're just curious now, this owner gives another survey, the same survey, I should say, let's just say same survey, but to another N customers. We wanted to predict how many out of them gonna prefer Friday as well. So mathematically, it is a conditional distribution over here. We call it predictive distribution. It's going to be Y tilde given or conditioning on the fact that capital Y equals to little y. This is the previous round of the data that we get. For any of you who are interested, the exact solution follows what we call a beta binomial distribution. As you can see, it's kind of complicated. I won't get into too much of the detail over here, but there will be a lab about this coming up. So we'll revisit this exercise later. But for us, and you will see again and again throughout, that whenever we're trying to do prediction, we're most likely going to do it through simulation. And I want to say that in that case, it is actually pretty straightforward using Bayesian method. So let me show you this exercise first, and then show you what we mean by straightforward and all that. So if we're just trying to predict, okay, we're trying to take a value, or actually try to get a value of this Y tilde, right? And if we already know the posterior distribution of P, as we know, is beta A plus Y and B plus N minus Y, all we need to do, if we want to do a prediction, is I just need to first get a sample of my posterior P. So I sampled it from R beta. In this case, you're going to see that we use our little r beta in R in order to get a random draw. And then given whatever the p-value, sorry about the term, the value of p that we're able to get, we're just going to do another sampling from the binomial distribution of n as the number of trials, and then whatever the draw that we have from the previous step as the success probability. Okay, so the logic goes this way. I want to predict my y tilde. Okay, and I know my y tilde, well, I already know the posterior distribution of p, and I want to use that information. Okay, so I do this through a two-step process. I need to have a posterior sample p, like a particular value of p that I can sample from this posterior beta distribution. And then given whatever the value of p that I got, I can do another binomial draw. So that's R binom. We're going to see the sample code coming up. But specifically, remember, the survey now is sent to m people. Okay, so just be careful. We're setting the total number of trials or whatever the value is as m. And then the p value that we're working with is from the previous step of the sampling. So you're going to see again and again, like I said, throughout, that the Bayesian prediction is kind of straightforward. You need a parameter draw, or you need a draw or a value of the parameter, and then you can take another draw from the data model. So in our case, we take a posterior draw from the beta posterior distribution, and then use that number. We're able to take a y tilde from the data model, which once again is the binomial because we have fixed number of trials, which is m, and then we have the value of p, which is the success probability in the posterior. All right, so the code, maybe show you a little bit, so hopefully a little bit more easier to contextualize. So when you do predictions, once again, you kind of need to determine how many times you want to do the predictions and everything and all that. So let's just say it's 1,000 again. We have our A and B. So here, I didn't use like the posterior values of the shape parameters, like the sum, I think like the 15.06 and 10.56, but I just put down the prior shape parameters and also the data. And here, I guess I'm giving the illustration of what if I'm giving it out to another 20 people. So my n and m in this case are the same values, but not necessarily, okay? Because m can be a different size if you're giving to a different group of customers, and then it's a different size, that will be fine too. All right, so the main chunk of the code over here is this. I want to, let's see. So first of all, so let me go back quickly here. So like I said, it's a two-step process. You first generate the value of p from its posterior, and then you generate a new y tilde given the value of p that you draw from the posterior from a binomial draw. So the main chunk is this R beta and the R binom. Okay, so R beta, like we talked about, is random draw beta distribution. And I'm doing it for like S number of times. And I'm drawing it from A plus Y and B plus M minus Y. So this are just really just the posterior shape parameters. So when I do that, I'm going to get, I think S number is a vector. Okay, I'm going to get predicted Y from the simulation. Oh, sorry, predicted P. It's S of them, which is 1,000 in our example. And now I want to, for each of the draws that I have, for each of them, I want to draw a y tilde. Okay, so for R binom, so R again stands for random draw. Binom is the binomial distribution. We need to specify how many draws we want. We need to specify the number of trials, which is m in our case. And then we also need to specify the success probability. Okay, so everything, these two lines, both of them will work with vector. Okay, because we have a vector of predict p sim, and then we also have a vector of predict y sim. And that's the p that we're working with earlier, and this is the y tilde that we're able to generate. So over here, I guess I was trying to also illustrate, I want to know how much what's the posterior probability that I get my prediction between 5 and 15. So in that case, I can summarize by doing this logical operation, and then that is going to be 87% predictions going to be between 5 and 15. So this is like, you can think about the question as what is the chance, or what is the probability that when you give the survey to another 20 people, we have 87% chance of having between 5 and 15 responses saying yes to preferring Friday. Kind of makes sense? hopefully. Yeah, so the procedure, like I said, is a two-step process. We do it one by one. And then the R code hopefully is matching, like I said, the process one by one that we talked about before. And then eventually you should be able to do some kind of summary if you're trying to answer specific questions. Okay. All right, and I should also say, like I mentioned earlier, that the exact solution of this prediction is a beta binomial distribution. Don't worry about it too much right now, but I just want to show you, you can also get the exact solution because we know that fancy distribution is, so we can actually compare the exact and the simulated. As you can see over here, might not be as close, okay, because you can see the peak, for example, in the simulated, which is what we talked about, the two-step process, we're getting, I guess, a peak around, I guess, 11-ish, right? Over here is a little bit 12. So it's a little bit more shifted to the left. So other factors affecting all of this, I think mostly, again, is the sample size, which is the simulation sample size, which will be that capital S. So if you increase that, overall, we should be able to have a better approximation to the exact solution from the simulated solution. All right, so the last concept, which is, like I said, we can do prediction and everything, that's all great, but we can also use that to check how good our model is. And when that is being done, we have a particular term for it. We call it Bayesian predictive checking. So the checking part is checking how good our model is, okay? So the general concept, as you can see, is still based on doing Bayesian prediction. So this is what we covered just now, okay? If I have my posterior distribution is this, and then I want to get a new prediction value, I just need to get first a sample of P and then use that in my prediction coming up. If I'm trying to use the same concept to check how good my model fit is, the caveat or the highlight over here is that, well, when we're doing prediction like that, we should be predicting exactly the same number of trials as what we have in the sample. Okay, so earlier I used M, okay, you can use like 20, 30, 40, whatever values, it doesn't have to be the same as M. But if we're trying to use this general strategy to check how good our model is, we are essentially replicating our original sample, okay, by doing prediction. Because of that, we're fixing the number of trials that we're doing as the same as the original sample size. Okay? So the general idea of the checking over here is that, well, I have this particular sample. If you remember, our data N is 20, right? And Y is 12. And what we're trying to do is now we have a posterior distribution of that data, what, 15.06 and 11 or 10. Whatever 6 over there. So we want to just see how good that is describing, you know, what we saw in the observed sample. So all we need to do is we do this for a large number of times, as you can see over here. And more importantly, we're trying to replicate the same size as the sample as before. And we want to see that, well, if we're doing that, all of the white tildes that we're able to get, we can check how close that is to 12. Okay? So 12 is the observed sample, right? Is the observed number of successes in the sample. And through this, what we call posterior predictive checking process, we're able to get a large number of the predicted values using the same number of trials, which is 20 throughout. And then we can check how close this predicted values to our actual Y, and that can give us a sense of how good our model is. Okay? So this is, like I said, what we call posterior predictive checking. And you can think about this whole sample that we're able to get is an approximation to the posterior distribution, posterior predictive distribution that we're able to use later on. So without further ado, I just want to show you the code so everything hopefully can be a little bit more contextualized. So once again, we have our S, the number of simulations, our A and B, the original sample size, N and Y, as usual. And this is really just like a coding preference. You can do whatever you want. For me, I think just for later, I can plot it. I create a data frame. And you can see that, well, the data frame is really just a bunch of NAs with the same length as how many simulations we're doing. And so those are really just for plotting. So I do that. But the main part, as we saw before, is you have to, first of all, do your R beta. And then you have to do your R by norm. And then you have to record whatever the value is. The difference, as you can see over here, is that we're writing a loop. Okay? We're looping through all of the different iterations of like capital S number of them. So within each, we only need to draw one P and then one Y tilde. Okay, so let me go back to the previous slide really quick. So you see that in the previous slide, we're trying to write them row by row. Okay, so for the first simulation, I'm getting a P1, and then from P1, I'm getting a Y tilde 1. And then I need to do another one for P2, and then I get that for Y tilde 2, et cetera, et cetera. So because of this structure, because every time we're trying to make a prediction only about one Y, given whatever the P that I have. So when I'm writing a loop, I'm looping through all of the process. And because of that, every time I only take one sample of P, and from that, I only take one sample of Y tilde. And that's what this code is showing you. That's why I was trying to highlight over here, the 1 and 1 over here. Okay. If we compare to what we did before, that, okay, I'm not really interested in checking, like doing the checking itself. I just want to get 1,000 different predicted values. Then I can do the vector manipulation over here. Like I said, we can actually altogether generate 1,000 different betas, and then from there we can get 1,000 different Y tilde. But that's for only doing prediction. I just want to have S number of predictions, and that's what you can do. However, if you are ever doing checking, once again, the key is that we are trying to replicate S number of different samples, replicating the original observed sample. So because of that, we are doing them one by one. And because of that, the code shows up as a loop. Okay? And then within each, you're only doing one at a time. Okay? So I'm highlighting here, maybe you don't think they're very different, but once you start doing it, it's very easy to make mistakes of thinking, well, when to use S, when to use one. I think you will get some exercise and practice over there. But I want to highlight this easily mistaken part, just to contrast between if you're doing predictive checking, it's one thing, you're doing this with only one draw within each, but then you're looping through the whole thing for S number of times. But if you're just trying to get S number of predictions, then you don't need to loop in the first place, and then you can use vectorized manipulation or calculation to get things pretty quickly. So let me show you. So the ggplot to do this. So really, I was doing a histogram, I guess, of that S, which is 1,000, I think, different posterior predicted values of this Y tilde that I can have. And so it's this histogram over here, and then I try to use a large red dot to show you the actual Y. Okay, so the actual Y, which is 12 in our example, we know is over here, and you can see how that compares to, or I should say, how all of the predicted Y tilde from the prediction or predictive checking compared to this. Okay? So maybe just given your own reading of this, I was curious. So here it's kind of in the middle, right? Kind of in the middle. So it's overall saying that, well, if we do have our posterior distribution as that beta, I think is what, 15.06 and 10.56, something like that. If we're indeed using this or arriving at this posterior distribution of beta, of P, of this particular beta posterior distribution, it seems reasonable, I guess, in a sense that because if we're doing prediction using this posterior distribution, we are getting a nicely looking overall, I guess, and close to the true Y compared to the simulated Ys. So overall, I think this is suggesting that the model fit, meaning that we're using a beta prior and everything, and combined with the data to do the inference, overall, it seems reasonable to use. Of course, when it could be not reasonable, so I don't have it as a plot to show, but I can, for example, illustrate, use a different color here. But let's just say, if you get a histogram of your predicted value, and once you add whatever the observed value, if it's very extreme, something like here, or something like here, then that is probably telling you that the model is not really describing the data too well. Okay? Because what that means is that, well, I have whatever my posterior distribution, and I have this histogram going, but my actually observed value is probably, well, is very unlikely to be observed if indeed my posterior distribution is real or is true, then in that case, that will be relatively evidence against what you have done. Okay? So of course, you'll be wondering, well, what else can we do, right? The data doesn't change, so data will be fixed. It's always like n is 20, y is 12, something like that. When this happens, like when the green ones really happens, that probably suggests you to use some like a different prior or something. Okay? Meaning that the prior maybe is playing too much a role in your Bayesian inference process, that the data has too little influence, sorry. And when that happens, you could adjust things accordingly. Okay. More formally, like I said, you can actually compute the posterior probability of the predicted, like the actual observed value greater than the predicted, or 1 minus that. And if either of them is really small or really large, that will give you a sense of not really good fit. Okay, so what I mean is you can compute the probability of this area and also this area. So if either of this is very small or very big, like the green dots that I showed you earlier, then that is suggesting that the model fit might not be really good. You might consider something else. But in our case, they're actually very close to, both of them pretty close to 50%. So it's also what we saw in the graph. It's kind of right in the middle. So that also gives us, justification that overall this model seems to be fine. Okay. Okay, makes sense. All right, so I think to recap, well, we talked a lot about different inference techniques, and in particular, how you can do exact solution versus simulation-based solution. I think this is really what the fun part starts to get into it, because once you can do simulation, there are many different ways you can summarize and work with the posterior distribution. So to recap, we talked about the 3 general steps, right, of Bayesian inference procedure: the prior, the data/likelihood, and then the posterior. We talked about why we say that the Bayes rule can help us sharpen and update the previous opinion from the sample, meaning that from the prior and the data to the posterior, like the sharpen part, so we have less uncertainty. And the mean, as we can see, is an average between some kind of average, right, between the prior mean as well as the sample mean. And specifically, we work with this binomial data likelihood function. So the beta distributions, they are conjugate priors. So what that means, the general result that we have covered is if we have a prior to be beta AB and our sampling density is binomial MP, then the posterior is going to be another beta of A plus Y and B plus M minus Y. And this could be used in any kind of context if you're using the beta prior for a sampling model of binomial. And that's why sometimes it's useful to code, like not to hard code the values of A and B into like A plus Y and B plus M minus Y. You can just like always write a general function when you do it, and then you can supply the values of A, B, and Y later on if you want to make your R function more general. But again, that's just a preference thing, and you should always do what works for you, and you will learn through the process as well. And the last comments or the topics we covered is the inference methods and techniques. For all of them, we talked about the exact versus the simulation-based method. Hypothesis testing, credible intervals, predictions, and lastly, the predictive checking. They are very useful, and we will see how that can be done in some other more complicated models as a way to check how good our model fit is. Okay, sounds good. Most of you, questions, comments? All right, a bit quiet today. All right, that's totally fine as well. So let me